So when I was talking about strong inference, I've talked a lot about accepting or rejecting hypotheses, and I didn't talk about what criteria we used to do that, and we use test statistics. So each of the different statistical tests that we will study has what's called a test statistic associated with it. People used maximum likelihood in calculus to compute what that test statistic should be for that situation, and that made the computations easier than if you had to compute the likelihood for every possible alternative model. So we find the probability of observing our test statistic according to the null. So our null hypothesis is going to have some expected value, and the farther our test statistic is from that expected value, the less likely we are to see it, or the lower the probability there is of that test statistic given the null hypothesis. And if that probability is low enough, we reject the null. So clearly it's terribly low here, clearly it's not very low here, and there's this intermediate range that we have to figure out what to deal with, and that's what the rest of this lecture is about. So what we do is we compare our test statistic to the expected value. And the farther our test statistic is from the expected value, the less probable it is if our null hypothesis is correct. So say our null hypothesis is this. If we expect to see, if our null hypothesis is that the test statistic will be greater than or equal to 0, so then maybe this is the negative slope where we expect lower tomato meter readings for more Jedi. And the probability, so that means that over here is what our null hypothesis would predict, right? So a slope of 0 or a positive correlation, meaning more Jedi is better, we expect to see these in our null hypothesis. So if we observe something here in our data that's not very strong evidence that our null hypothesis is wrong, but as we get way out here, be like, okay, we'd hardly ever expect to see this if our null hypothesis is wrong. So this red curve is showing the probabilities of those things. Similarly, if our hypothesis was for our test hypothesis was for a positive relationship, then the null hypothesis would be looking for stuff in the negatives, and that the higher our test statistic was, the farther it was from the expected in the null case, the lower the probability of observing that test statistic would be. So it turns out that the stronger the evidence is for our research hypothesis, the lower this probability is. So that's something that's a little counterintuitive for people. Another thing that can be counterintuitive for people is that we have tails. So you saw before here that the research hypothesis was negative, and so the farther we got away from negative here, the less likely the null hypothesis was true. And then the direction changed and went this way. So each of these are one-tailed. This is the red one's a negative one-tailed, and the yellow one's a positive one-tailed. And so that's what this looks like. So if we see results out here on the positive end, then we think, and this is the distribution we expect if our null hypothesis is true, then we might reject our null hypothesis. And then again, if our research hypothesis is that we expect to see a low number, and this is the distribution of results we expect from our null hypothesis, then we would ultimately reject the null hypothesis if things are low. So this is important, right? If our hypothesis is that there's no relation, is that Jedi hurt the film, and we see there's a really strong relationship with the more Jedi, the better the film does, then we wouldn't reject the null hypothesis. We'd say, yeah, Jedi don't hurt the film. Finally, though, we might have situations where there are two tails, where we don't know beforehand whether we think the hypothesis is negative or positive. And so any test statistic that's far from the expectation, whether it's below or above the expectation, will be significant. And so in these two-tailed situations, the area under the curve has to do with how likely we are to reject the null hypothesis. And so you can see how this has moved a little farther away. That area of this red plus the area of this red over here, those added together are equal to this one by itself or this one by itself. So you have to be a little farther away from the center in order to reject the null hypothesis if you have a two-tailed hypothesis, when positive or negative could be reasonable. So positive, our research hypothesis requires that our test statistic is greater than 0. Negative research hypothesis that our test statistic is less than 0 or expected. Two-tailed could be greater, less than, or greater than. So that vertical line there in the shaded red area, those are previews of critical values and alpha. So both of these two things here take a lot of calculations. Finding these curves used to be really hard when people had to use slide rules and pen and paper to do calculations. And if we compute this red thing based on our test statistic, we only need to compute it once. And then we don't need to recompute it for new data. If we're computing the likelihood, which is kind of like what we get with this one, where we'd say what's the probability of observing each value, that we have to compute for every analysis. So folks used approach 1. And that creates critical values. So we'd say, let's pick a value so that we have we only have a 5% chance of rejecting the null if our test statistic is this big or smaller. So the area under this red curve here, that's the probability of observing a value this big or less. I'm sorry, it's the area under the blue curve, it's the actual height of the red curve. That's our probability of observing a -2 or less given this null hypothesis. And so if we pick it at 5%, that means we only commit type 1 errors 5% of the time. So alpha is also called the type 1 error rate. And it gives us the notion of statistical significance. So statistical significance is the probability that we're seeing something that isn't there. It's the probability of committing a type 1 error. It's the probability of observing our data in a situation where the null hypothesis is true. It's the p-value. So it's this number that people like to look at and use in stats, but it's actually a fairly complicated little bugger. So, for example, if you have an alpha value of -3, oh, that's wrong, that's the critical value of -3, and then the p-value, oh, I need to change that. That's too bad. That should say alpha, that should say critical value, that should say alpha, that should say critical value. I will change those shortly. And that's annoying also. I'll probably have to change that slide a bit. Okay, so this is what I should have talked about before. And so going from alpha to the critical value uses the norm.inv function. If we have alpha is 0.05, so we're willing to tolerate a 5% type 1 error rate. Our null hypothesis, our sample comes from a population that's normally distributed with a mean of 0.5 and a standard deviation of 22.1. Then you can compute your critical values this way. So there's our one-tailed critical value. And then, like I said, we have to divide our alpha by 2 to get our two-tailed. And then the opposite direction is critical value is 3.14. Your H0 is the sample that comes from population. This should probably be a 2 rather than a 0.5. So you can compute those that way. So that's how it works with the normal distribution. Here's how it works for the other distributions we'll use. So we hardly will ever use a normal distribution. We'll use a student's t a lot whenever we're comparing the means of two groups. We use Pearson's chi-squared when we're looking at observed minus the difference between observed and expected in discrete variables. And we use Fisher's f when we're comparing the means of more than two groups at a time. So you can see they have similar sort of format where you have the name or abbreviation of the distribution, and then .dist, and then the critical value, which is x, and then some extra parameters, and then true because you want the cumulative distribution. That's how you get the alpha value from the critical value. And if you have a critical value, if you want to compute the critical value from an alpha, then it's the distribution.inv and the parameters, and you don't need the trues. So that is it. That is a lot. You're going to do great, though. I'm confident of it.